Hello, my name is Rachel Reika. I am presenting on my Group 5 project for the Combined Spectral Problems for the Organic Chemistry course. So here we can see the Combined Spectral Problems worksheet. We'll primarily be working off of this, but I will also be showing the work that I did on my PDF handout. First thing that we notice is the molecular formula. The molecular formula is C4H6O2. Now that will indicate 4 degrees of unsaturation. And the way degrees of unsaturation are calculated is by taking the number of carbons that we have, multiplying that by 2, and then adding 2. So if we had a fully saturated molecule, we'd expect to see 10 different hydrogens. We only see 6, that's 4 degrees of unsaturation. To us, the first thing that indicates is that either we have 2 double bonds going on or we potentially have a ring structure that is formed. So let's go ahead and analyze our first spectrum, which will be this IR spectrum here. The first place we'll look is over here. This will be all molecules bonded to H. Right here, we can see 2 little peaks just at about and below 3,000. Now that is going to indicate to us an sp3CH bond. If we had an sp2CH bond, we'd see it slightly above 3,000. We see it a little bit below, so that's sp3. We also see a little nubbin of a peak over here. This peak doesn't really fit well into anything that our molecular formula has given us so far. If we saw oxygen bounded to hydrogen, we would expect to see a broad, wide peak here. Or we could see nitrogen bonded to hydrogen also showing up in this region, but there's no nitrogen in our molecule, so we're going to leave this peak out for the moment. Next thing we're going to look at is this very large peak right here at about 1750. This is a classic peak that indicates a carbon-oxygen double bond, so a carbonyl bond. So that's pretty obvious right there, pretty in your face. The next one that we're going to go ahead and look at are our peaks over here. We're seeing a large one again at 1,150, so 1,150. That is going to indicate to us a carbon and oxygen bond. Below 1,000, we see the fingerprint region. We don't really pay a ton of attention to that. We're seeing just a couple of other peaks in here. Most of that is just, we're looking mainly at this carbon-oxygen bond here. All right, so moving on to this 13C NMR spectra, we're going to notice first thing that we have 4 peaks. That indicates that we have 4 unique carbons. So there's no symmetry going on within this molecule itself. We've got 4 unique carbons here. The first chemical shift that we will notice is at 180. Now that is a classic diagnostic peak for a ester bond. So in a carbon that's double bonded to an oxygen and also has a single bond to another oxygen. So you can see right here, a handy dandy piece of paper that I've drawn exactly that. Oxygen, double bonded to carbon, single bonded to oxygen. If we had a carboxylic acid or straight carbonyl, we'd see that a little bit higher. But at 180, we expect to see the ester. Then we see our next peak at 70. That is going to indicate our carbon-oxygen bond. That's again a really diagnostic area between 80 and 40 for any kind of carbons bonded to a more electronegative atom. Below 40, we start to see our carbon-hydrogen bonds. However, we see a peak at 28 and then again at 20. We know that CH2 is going to be more downfield than a CH3 carbon because of the deshielding involved in that. So the carbon that we see at 28, that's going to be our CH2, and the carbon we see at 20, that's our CH3. So again, I've got that indicated here. For the 28, we have CH2. For the 20, we have CH3. Okay. So moving on, now that we have determined all 4 of the peaks for our 13C spectra, we'll look at our 1H NMR spectra. So this spectra is giving us a lot of information. The first is that we only see 3 peaks. So we know that there are only 3 unique hydrogen positions in this molecule. At this point, we're thinking about a couple of different structures. One potential structure we could be considering would be something that's linear. So we could be considering a linear ester. So we have 4 carbons in there along with a carbonyl and an ester. However, if we count up the hydrogens in this molecule, we'll see that we have too many. 3 hydrogens here, 3 there, 2 there. That will total us out to 8 hydrogens. We only have 6. We know, therefore, that there either has to be a second double bond or there has to be a ring structure that we're considering. We know that we are not looking at a second double bond because in our IR spectra, we don't see any of the double bond signaling for a carbon-carbon double bond anywhere around the 2000 range. All of that's just noise. So we know we're not looking at a carbon-carbon double bond. We know that we have to have an ester, so that's a carbon, a carbonyl connected to an oxygen, just like that. So that doesn't leave us room to have 2 carbon-oxygen double bonds. So that means we must be considering a ring structure at that point. So let's continue on with the 1H NMR with that in mind. We have 3 unique hydrogen locations. They're all integrated at 2H is the integration. So that means that each of them, they'll have 2 hydrogens on them only. So again, if we're thinking about a ring, all of this information is starting to fit. So if we're looking at a ring instead of what we were just looking at, which was the linear molecule, we'll see that this does fit with our new theory of having a ring. So we can see here that we have 1, 2, 3, 4, 5, 6 hydrogens in 3 unique positions. So that fits with our NMR data and our C13 data, but let's continue analyzing the NMR as we look at this structure. So over here on the far left, we have a peak at 4.5 and it's a triplet. That means that the on the carbon next to it, that carbon will only have 2 hydrogen molecules. Because it shifted so far to the left at 4, almost 4.5, we're considering that this is going to be the carbon bonded to the oxygen and the hydrogens on it. So right here, so this carbon bonded to oxygen and the 2 hydrogens on it, that's what's represented by the peak on the far left. And that's because the oxygen is deshielding, bringing it further downfield. Now we go over here to the right. The peak on the farthest to the left we see is at 2.4 or so. And that's also going to be a triplet. So that's going to be this carbon right here. It's connected to a carbonyl carbon. So that's going to further downshift it, but not as much as if it were directly bonded to an electronegative atom. Again, it's got a triplet. So that means that there's no hydrogens up here and there are 2 hydrogens right adjacent to it. Finally, we'll look at the last peak at 2.1. There we see 5 different peaks. That means that on the carbons next to it, its neighbors are going to have 4 carbons. I'm sorry, excuse me. On the neighboring carbons, there are going to be 4 hydrogens because it's a quartet, 5 peak, I'm sorry, quintet, 5 peaks. So the n-1 rule tells us that, I'm sorry, n+1 rule tells us that that is going to have 4 hydrogens on the neighbors in that case. So that fits with what we figured out for this carbon so far. 1, 2, 3, 4 neighbors. That fits exactly with this molecule. All of our information has come together. We have analyzed it all in this handy dandy little table and confirmed that indeed we are looking at a pentagonally shaped ring with an ester molecule in it. This fits with our degrees of unsaturation, with the molecular formula itself, and with all of the information we have analyzed from our different spectra. Thank you so much for coming to this talk. All right, thank you.